Hello everyone, and thank you for tuning in. I'm Vamsi Karanam, a senior software engineer. In this session, I will walk you through a simple but powerful idea. What if you could define and run an entire quantum experiment from a single JSON file? No more cloning notebooks, updating brittle scripts, or writing pipelines by hand. Instead, we will explore a schema-driven approach that helps researchers move faster, build repeatable processes, and gain built-in observability. This is all without writing front-end or orchestration code. Quantum research moves fast. New hardware, circuit designs, and error mitigation techniques emerge constantly, but our tooling often lags behind. Copying notebooks create fragile dependencies. Documentation drifts as experiments evolve, and auditing becomes nearly impossible. This slide captures the problem. Constant change in parameter and hardware, hidden dependencies and logic buried in scripts, inconsistent documentation, and a serious compliance headache for regular industries. To solve these challenges, we built a schema-driven framework. At its core is a single JSON schema, a machine-readable contract that defines what an experiment can and cannot accept. From this schema, we auto-generate three things. First, a React-based web form, so scientists never touch HTML or JavaScript. Second, a step functions workflow to execute circuits and post-process data, all serverless. Third, a lineage tracker. Every run is tagged, versioned, traceable. This means researchers are just a manifest, not a monolith of scripts. Here is how it all fits together. The JSON schema is stored in AWS S3 with object lock enabled, ensuring it is versioned and also immutable. A CI/CD pipeline triggers two generators. One builds the React portal, the other compiles a step function state machine. The state machine calls Amazon Bracket to run quantum jobs, invokes Fargate containers for post-processing and stores results in S3. Observability is handled by OpenTelemetry with the dashboards in Grafana. This system is modular, serverless, and also designed for scale and traceability. On the right side, you can see the architectural diagram and the components involved. Let's compare traditional workflows with our schema-driven approach. On the left is a notebook model. Everything is hand-coded, the device, on, circuit shards, and output path. It works, but it's fragile and error-prone. Also, every time some parameter has to be changed, this notebook model has to be updated. On the right is a compact JSON schema, 30 lines that describe the entire experiment setup. The schema is used across the UI, the workflow, and the validation logic. Instead of cloning and modifying notebooks, research fill out a form that is guaranteed to be a valid one. This approach unlocks four big benefits. First one, parameter exploration becomes safe and structured, no invalid values, no runtime surprises. And the second one, collaboration improves. Schemas are versioned in Git with pull requests and differences. Number three, configuration errors go to zero because schema validation runs upfront. Four, onboarding is dramatically faster. New team members don't need to learn your SDKs or internal scripts. They simply open a form and run. You get governance without sacrificing speed. To test this in real world, we ran a 1 million shot VQE sweep. This bar chart shows the results across 5 metrics. Let's walk through it. On the far left, setup time, the time to prepare a single parameter variant dropped from 18 minutes with notebooks to just 3 minutes with a schema portal. Next is wall clock time, total runtime for the entire sweep, which dropped from 13.4 hours to 11.8 8 hours. That improvement comes from better concurrency and simulator fallback when QPU queues are long. Third is a configuration errors. We went from 7 errors in the baseline to 0, which is a huge win. Then cost. The schema workflow saved around 200 USD, largely due to more efficient execution and fewer retries. Finally, learnability. Researchers rated the schema portal 4.8 out of 5 compared to 3.1 for the notebooks. Here, the learning is basically straightforward for the researchers. These aren't synthetic benchmarks. They are based on real world jobs running on a bracket with simulator fallback and post processing in Fargate. From an engineering standpoint, this system is compact and maintainable. We use three CDK stacks, one for front end portal, one for the state machine pipeline, and one for observability. The schema file itself is tiny, about 375 bytes. The React bundle is 1.2 KB after it's shipped using a gzip. The state machine is 6 KB JSON with 23 states, 5 service integrations, and no Lambda functions. We test locally using local stack, deploy with GitHub Actions, and run cost effectively within AWS free tier for most dev and test scenarios. This is just the beginning. We are expanding in 3 major directions. First, enabling multi-schema chaining so teams can compose multi-stage pipelines where output from one experiment feeds into another. Second, I'm adding post-quantum encryption. The results will be automatically encrypted with Kyber, aligning with NIST post-quantum standards. Third, we are making workflow cloud portable. We will support the backend Azure Quantum, Google Circ using the same schema and UI. This will let researchers focus on science, not the infrastructure. Thank you for spending time with me today. Schema-driven experiment portals bring structure, automation, observability to quantum research without slowing scientists down. You gain auditability, cost control, and repeatability while freeing your teams from fragile code. If you are working on quantum workflows, I would love to connect and share code patterns or blueprints. Thanks again and enjoy the rest of Conf42 Quantum Computing 2020.